Okay, for this problem here, it says a water jet of velocity Vj and thickness dj impinges on a turning block which is held in place by a force f of x, as shown in the sketch. As the water leaves the block, the round jet flattens and slows down due to friction along the wall. The water turns a full 180 degrees and flattens into a rectangle shape with thickness dj over 6 and a width of 10 dj in cross-section. The flow is steady. So the first thing we're going to do is we're going to get our assumptions. So the assumptions we're going to make in this problem is that the flow is steady, or steady flow, and we're going to make the assumption that it is incompressible. Just like that. So next what we're going to do, it's already drawn it out here for us, but I'm going to go ahead and draw it as well, is we're going to identify our control volume. The control volume that we're going to use goes around the entire block, as you can see here, and it's also going to make sure to include the inlet of water and the outlet of water. That's very important. So to bring that down here so we can see it a little better, it's going to look like this. So from here, the first thing that we're going to do is we're going to identify our vectors going into the control volume. So the first one is our velocity vector going in, and instead of calling it Vj, I'm just going to call it V1 to keep it simple. And then we're going to have our velocity coming out, which is V2. The other thing we're going to identify is our normal vector. Our normal vector is going to look like this, and it's normal to the control surface. This is going to be N1, and this one down here is going to be N2. The control surface is this side of the control volume that we have down here. The whole thing is a control volume. So from here, what we're going to do is we're going to take advantage of the conservation of mass principle and the conservation of momentum. So the first one we're going to start with is the conservation of mass, which looks like this. Control volume of density dV equals the control surface in of density times the dot product of the velocity vector times the normal vector, dA, this one's negative, minus the control surface out times the density, velocity vector dotted with the normal vector, dA. So going back to our assumption, since the flow is steady, that means that this term on the left-hand side actually goes to 0 because it is steady. So to rewrite this equation, I'm just going to do this. I'm going to copy it really quick. It's going to be 0 equals this. So from here, we can also fill in this dot product that we have. So the dot product is u is the velocity vector, so that's going to be our v1 and our v2. And then the n dot is going to be a normal vector. So to rewrite this equation again, it's going to look a little something like this. We're going to erase the velocity and normal vector. So our velocity vector, that's just going to be v1. And then it's going to be dotted with our normal vector, which is going to be cosine, and then the angle that it makes with the control surface. So in this case, it's going to be an angle of, right here, it's going to be 180 degrees or pi, just like that. And it's going to be the same thing for this guy over here. Something to take note of is that now the velocity vector is going in the opposite direction, so it's going to be a negative v2 dotted with a cosine of pi again. So from that, we know that the cosine of pi is negative 1. So that negative 1 is going to cancel out this negative here, and then the negative 1 that comes from this, that's just going to cancel out with the negative that you get from the velocity vector. So to rewrite this equation one more time, we're just going to get 0 equals the integral of the control surface in times density V1 dA minus the control surface out density V2 dA. Now solving this integral, we're going to take the integral with respect to dA with respect to the area. So that's just going to give us an A. So 0 equals density V1 A minus density V2 A. Just like that. We can rearrange this equation to get density V1A equals density V2A. And this relationship right here is really important because density times velocity times the area is actually the mass flow rate. So what we get from this relationship right here in the conservation of mass is that the mass flow rate in equals the mass flow rate out. So the mass flow rate that is right here equals the mass flow rate right here. So continuing on from that, we're going to take it a step backwards, and we're going to take this equation right here. So let me go ahead and copy that and write it again. This equation right here, and we're going to actually be solving for V2 here. So rearranging that, the first thing we can do is we can cancel out these density variables because, as I said earlier in our assumption, it's incompressible. So our density is going to remain constant. So then we're going to have, we're going to have V1 times pi over 4 d1 squared equals V2 times 10 d1 times 1/6 d1. So this term right here is the A, because we know that the inlet area, this AJ or A1 in our case, is going to be the area of the circle, which is just pi r squared, or pi over 4 d squared. And then this right here is also our A term. This is our A2 term, which is just the cross-sectional area of the stream when it exits here, which is 10 dj or 10 d1 times d1 over 6. So that's where those terms come from. So then now that we have all of our terms and our variables, now we can solve for V2, which is going to look like this, which is going to be 3 pi over 20 V1. And we're going to get it all in terms of our variables here first. We're going to get it as simple as possible because the problem does not give us any numbers to work with. We're just going to be solving the equation using the variables that we're given. So now that we have this velocity term, now we can use the conservation of momentum. That equation is going to look like this: d dt of the integral of cv. I think I have it copied. I do not have it copied anymore. So I'll just go ahead and rewrite it. Density dA equals the control surface in negative density velocity vector times the velocity vector again dot with the normal vector dA minus cs out density velocity vector dotted with normal vector dA plus the sum of the forces. So similar with the conservation of mass, this term on the left-hand side is going to go to 0 because it is steady. And then to rewrite this equation again, this time I am going to copy it. this is going to equal 0. And then from here, we can do the exact same thing again. So to copy it again, we're going to get it here, and we're going to solve for this dot product again, like we did earlier in the conservation of momentum. So to erase these, we'll pull this over here, and this one as well. This is going to be V1 times V1 cosine pi dA times V2 V2 cosine pi negative V2. And then the sum of the forces that we could have the force of gravity, we could have applied forces, but in this case, the only force that we have is the f of x that is given in the problem right here. And we're going to make that negative because it's going in the opposite direction as what we defined our axes to be. Our axes being y up, like that. That's why our velocity in is positive and our velocity out is negative. So then we can go ahead and do what we did on the last problem, and I'm just going to simplify that really quick. I'm not going to go to solve the integral. If you need help solving the integral, you can go up and watch how I did the conservation of mass integral. But this is going to result in us getting density v1 squared a minus density v2 squared a minus f of x. The conservation of momentum is going to have this squared term because we have two velocity vectors here. So just rearranging this equation, I'm going to get negative x f of x equals density v2 a v2. You'll see why I'm doing this in a second, minus density v1 a v1. So again, something that we can see here is that this term here and this term here is our mass flow rate. I'm not bothering writing 1 or 2 because we know that the mass flow rates are equal, as we proved earlier in our conservation of mass formula. So to rewrite this again, we're going to get negative f of x is going to equal the mass flow rate times v2 minus the mass flow rate times v1. And also this right here, this term right here, we need to remember that the velocity vector is actually negative in this case because it is going in the opposite direction of our velocity 1, or it's going in the opposite direction of our axes that we defined, which again was to the right here as positive. So as you can see, all these terms have a nice negative sign that we can eliminate. So now we can solve for our f of x. That's just going to equal the mass flow rate times v2 minus the mass flow rate of times v1. So to simplify this now, I'm just going to get the f of x equals the mass flow rate. Oops, this should be a plus, excuse me. Times v2 plus v1. Now, you remember we solved for v2 in terms of v1 earlier, so we're going to go ahead and plug in all the terms that we know. So the mass flow rate is going to be the density times v1 times pi over 4 d squared times v2, which was up here that we solved for earlier. So I'll just go ahead and copy that. It's going to be pi over 20 times v1 plus v1. And that right there is your answer to the resultant force that is going to hold this plate in place, depending on all the factors that go into the jet stream. So for example, if we wanted to give this some value, we could say that perhaps V1 equals 10 meters per second. Our diameter 1 is going to equal 2 centimeters, and from there we can go back to this equation that we just solved for, and we can say f of x equals the density, which is 1,000, v1, which is 10 meters per second, pi over 4. Our diameter is 2 centimeters, which is going to be 0.02 meters squared, times 3 pi over 20 times 10 plus 10. And then solving this, we're going to get that the force required to keep the block in place using these variables is 46.22 newtons.